We're going to be finding more antiderivatives. This time, there's another way that we're going to use to find some derivatives, because not all derivatives are just as simple as, okay, here's a rule and find a derivative. This is sort of the backwards chain rule whenever we're looking at it. It's not a rule where you just do the same thing every time. It's a method where there's a process and you have to use the process every time. It only works on problems that involve basically the chain rule. So the first kind of problem we're going to look at is the integral of 3e to the 3x dx. The reason this problem is not just as simple as what we've been doing is because in the power there's a 3x. And I know if I would have found the derivative, then the derivative would be e to the 3x and then times 3. So that e to the 3x has something to do with finding the antiderivative. Now some of these you probably could look at it and just tell what the antiderivative is, but some of them you can't, so I need to show you the process. The first thing you're going to do is you're going to create u. U is usually the thing that you would have needed to find the derivative of when you do the chain rule. In this case, and in the first few problems, u is the power. So u is going to be 3x. And then what you do is you find du. Du means the derivative of u. So the derivative of 3x is 3, and it was in terms of dx. If you want to put the dx there, that's fine. Now, when you look back at the problem, whatever you have right here, it has to be in the original problem. Like, see, there's a 3 right there, and it tells me du is 3, so that's a good thing. Then what you do is you go back and you rewrite the integral. You substitute what u is in for that. And since du is 3 dx, see there's a 3 in the dx, together that makes du. So what we do is we totally rewrite the problem, getting rid of the power and making the power just be a variable. After you do that, you find the antiderivative. The antiderivative of e to a power is e to the power plus c. And then you go back and you substitute what u was back in for u. So there's the answer. Again, that was one you might have been able to look at and just know the answer, but we got to do this process. And it's kind of a different process. Alright, let's look at the next one. This one's very similar. We have e to a power. U is going to be the power, because that's what I would have taken the derivative of in doing the chain rule. So then du is the derivative, which is 4. So there has to be a 4 in the problem. Well, there's not a 4 in the problem. We can, so what you can do is you can make there be a 4 in the problem. So you can put a 4 in. But if you have to put a 4 in, then what that means is that you have to multiply by 1/4 so that you don't change the problem. I'm going to put the 1/4 on the outside so as to make the problem a little bit easier to solve. So then we have a 1/4 on the outside. The 4 in the dx, see there's really a dx right there, that makes du, and then we have e to the u, because 4x minus 2 is u. So then we find the antiderivative. The antiderivative is e to the u, and you leave the 1/4 alone. And then you substitute what e to the u was back in. We're going to do several of the same kind of problems, and then we'll change it in a minute. So let's say on this one we have 5x e to the x squared plus 1. So this one looks really complicated, but actually it's very similar to the others. Still, u is going to be that power. Du is going to be 2x. Now this one's kind of strange because there's a 5 there. So totally just not worry about the 5 right now. We really want there to be a 2 inside. It says 2x, there's an x, so that's good. So we need a 2. So let's just put 2 in. Well, if I put a 2 in, I've got to put a half out, so that I make it just be 1. And this 5, what I'm going to do is I'm going to take it outside of the integral. You can take numbers as long as they're constants inside and outside the integral. It doesn't affect anything. So we're going to have a 1/2 on the outside, a 5 on the outside, and then an integral. Okay, it tells me we have e to the u. Okay, we took the 5, we took the 2 is part of du, the 2 and the dx is part of du. And see the 5 and the x, the 5 went out, the x was part of du. So this is what you end up with, 1/2 times 5 integral of e to the u. Then we have the integral of e to the u is e to the u, and then just bring down your 5/2 and then plug the u in. Now you can take the derivative of that if you want to realize that you actually get what you're supposed to, but you do. Okay, one more like that, and then we'll do a different one. Okay, just like the others, u is going to be, again, cosine, because that's the power. Du, the derivative of cosine, is negative sine. You put your little d theta if you want to. We have a sine, we have the d theta. The only other thing we need is a negative. We can put that in. But if we put one in, we've got to take one out so that we don't change it. So leave the negative outside. The negative, the sine, and the d theta, that makes du. And then you have e to the u. And then the antiderivative of e to the u, bring down your negative, is e to the u. And then plug in your u. Alright, all those dealt with u being the power. Well, u doesn't have to be a power. U can be, hang on, let's see, I don't think we're on number, we're on number 5. U can also be something else. There's several different kinds of things that u can be. Let's say that we have cosine of 2x. See, this one's different from yesterday, again, because of the 2x. So, think about the chain rule. We'd have to take the derivative of the 2x, so we're going to let u be 2x. That means du is 2. Well, there's not a 2 there, so we're going to put a 2 in. That means we need to multiply by 1/2 on the outside. So we have a 1/2 integral 2 and dx, that makes the du. And then we have cosine of u du. So then the antiderivative of cosine is sine. Plug in your u. And we're done. This one's very similar because it's still cosine. Again, think about the chain rule. You'd have to go back and take the derivative of that. So u is x to the third. Du is 3x squared dx. Notice 3x squared and dx is in there. I don't have to change anything. So we have integral of cosine of u. The integral of cosine is sine of u. And then substitute our u in. Okay, so we dealt with e to powers. We've dealt with cosine of something. Well, now we're going to look at what happens when you have something raised to a power. Now, on this problem, you actually could square it out and then find the antiderivative, but I want to show you another way, because if the power is much larger, the problem is totally different to solve. And so I want to show you how to do that. You can use this U-substitution method. You can let u be 2x plus 3. Du is 2. we got that 2, we got to put the 2 in, the 1/2 out. So that rewrites as 1/2 integral 2 dx makes the du, so then you have a u here, u squared. Then you can do that power rule, which I think you probably want to do at the beginning, but the problem is the thing inside the parentheses, the derivative is not 0. So then the power rule is 1/3 u to the third, and you just multiply the 1/2 by it. So that's 1/6 2x plus 3 to the third plus c. We can't say at the very beginning that that's 1/3 2x plus 3 to the third, and the reason is because it has to do with that chain rule when I find the derivative. So this down here is the answer. Alright, number 8. This one is similar. You would start off with letting u be x plus 3 and du being just 1 or dx. What that means is we don't have to change anything. This 4, you can just take it out here so it doesn't cause us any problems. 4 integral u to the 13th. Use the power rule, so that would be u to the 14th over 14, I'm sorry. You can reduce that, substitute in your u, and that's your answer. This one, the power rule would have worked just fine probably, and the reason is because the derivative of the inside originally was 1. Alright, u is still what's inside that parentheses. du is 3. We got this 2 in here. We're going to take it outside of it whenever we rewrite it. But basically we need a 3 in there, which means we need a 1/3 outside. So we're going to leave the 1/3. We're going to take out the 2. Then we have u to the 10th. And then the 3 and the dx make the du. So then we do the power rule. That would be 1 over 11, or u to the 11th over 11. So you get 2 over 33. Plug in your u plus c. Alright, this one's similar. I would suggest rewriting it as x to the 4th plus 5 to the 1/2 so that it looks like the others. And now u is going to be still the thing raised to the power. X to the 4th plus 5. du is going to be 4x to the 3rd. We're missing a 4, so we need to put 1 in. Take a 1/4 out. So we have 1/4 integral. 4x to the 3rd dx is part of du. X to the 4th plus 5, that'll be u. Then we do the power rule. 1/2 plus 1 is 3/2, so that'd be u to the 3/2. But then you divide by 3/2, which means times 2/3. So then we have 1/6 if you reduce it, times x 4th plus 5 to the 3/2 plus c. Another thing I want to show you is that this substitution thing doesn't always work. Look at this problem right here. U would be x to the 4th plus 5 because that's the thing like inside that would be raised to a power. But du is 4x to the 3rd. And in this case we're missing a 4 and an x. You can't ever add an x in there. You can always put a constant inside as long as you divide by the constant outside, but it can never ever be an x. So this one, there would have to be some other way that you would have to solve it. Alright, the last kind of problem is very similar, but sometimes it might be written on the bottom instead of as a power. And so I want you to see how that you could solve it. You could rewrite this one as 2x minus 1 to the negative 3, and then you can solve it the same way we just did. U is 2x minus 1, du is 2. So that would rewrite as 1/2 integral u to the negative 3, add 1, so that'd be negative 2, divide by it. And then if I multiply, that's negative 1/4 times 2x minus 1 to the negative 2 plus c. Here's another divided by, but since I have something on top and bottom here, I'm probably not going to rewrite it the way I did that last one. Since the last one was just a number on top, I rewrote it, but this one I'm not going to do that. If it's in this case, u is going to be what's on the bottom of the fraction. And this one's cool because, see, our e to the t is up there, so we know that we did that right. That means we have, you can write it as du over u, but I think it's easier to write it as 1 over u and then just put your du on the outside, because this part all makes the du. And then the antiderivative of 1 over u is ln of that, and then plus c. So that would have been ln of u. I skipped a step, I'm sorry. And then I substituted it in. Okay. Now this one doesn't look like the same kind of problem. We don't know the antiderivative of tangent, but if you rewrite it as sine of x over cosine of x, it becomes a similar kind of problem, and what I can do is I can let u be cosine of x. That means that du would be negative sine of x, because I'm taking the derivative. So the only thing I'm missing is a negative. If I put one in, I got to take one out. So then I have negative integral of 1 over u du, very similar. Antiderivative of 1 over u is ln of u. Plug in your u, and that's the answer. I know that this is more difficult than yesterday's, but it's kind of the same process. You have to find your u, find your du, figure out how to make the problem work out, and then solve it. So today I'm going to give you 4 kinds based on the kinds that I just showed you. And I just want you to try them. And I know that some of them will be easy for you to figure out and some of them will not be, but just see what you can do. And then we'll talk about these tomorrow.